Okay, class, in this video we're going to discuss a concept called activity. That's what goes in that gap there. Activity is an important concept in chemistry, and it is the relative ability of an element to give up an electron. We know that when we give up electrons, we become positively charged. And so basically this is saying how energetically preferred is it for an element to become a cation. We can rank the relative activity of elements in an activity series. So the activity series is a list that ranks the ability of a pure metal or a hydrogen to replace a metal ion or hydrogen in a compound, and we're specifically interested in single replacement reactions. So it says, look in the back of your periodic table. So I'm going to take the periodic table that we've given you, and we're going to take a look at the back of it. And on the back, you will find that there is an activity series of metals. And just because it says metals up there, it doesn't only have metals in it, because there's hydrogen as well. Now, we're mainly interested in looking for the neutral species. These are called half reactions, where you take an ion and you react it with one or more electrons to form a neutral species, like these neutral metals. So there's neutral lithium, neutral potassium, and so forth. And we're mainly interested in finding out where on this list the neutral species lies. And if we look down here, we will see that neutral hydrogen is right there. I want to emphasize the fact that we're looking for the neutral species because iron appears up here as a neutral species, and it appears down here as the ion. So we are not interested in iron here. This is where the neutral iron sits on the activity series. And the general rule is, the higher up on the list you are as an element, the more active you are. The more active you are, the more energetically preferred it is for you to become a cation. And the more energetically preferred it is for you to become a cation, the more you are going to energetically prefer to be in an ionic compound. And so if we go back here, let's fill in this gap here. The higher on our list that the pure metal or hydrogen occurs, that pure metal or hydrogen, that means the neutral metal or hydrogen occurs, the more active it is. I'd like to emphasize here that we are talking about activity and not reactivity in general. So reactivity and activity are very closely related, but for the purposes of this section, we're talking about activity. So let's move on to the next page. Now, as I say, this is a particularly important concept when we're talking about single replacement reactions, because fundamentally, it is the activity of certain species that is going to predict whether a reaction is going to take place. So here I've written a couple of examples. I have written zinc is going to be reacting with hydrochloric acid, and silver is reacting with hydrochloric acid. So let's take a look at these in terms of their activity. If zinc is more active than hydrogen, then zinc prefers energetically to become an ion. And therefore, zinc is energetically going to prefer to be in this compound more than hydrogen prefers to do so. We're going to look at our activity series and see where do zinc and hydrogen occur on the activity series. And if we look at it here, we can find that our zinc is right here, neutral zinc. And if we look for hydrogen, you will see that it's much lower. So it looks like zinc is more active than hydrogen. That means zinc does prefer energetically to be in an ionic compound more than hydrogen does. So, is this reaction going to take place? Is zinc going to be able to kick hydrogen out? Yes, because zinc is more active than hydrogen. So it's going to kick hydrogen out. Hydrogen is going to be its own standalone element. And when hydrogen is a standalone element, is H2 diatomic, and it's a gas. And now zinc is going to pair up with the chlorides, and we have a +2 zinc cation, because it's fixed charge at +2 whenever it's an ion. Chloride is a -1, so I need 2 of these chlorides in order to balance that zinc. Now I have the correct formulas. Now I have to balance it. 1 zinc, 1 zinc, 1 hydrogen, 2 hydrogens, 2 hydrogens, 1 zinc, 1 zinc, 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. It's completed and balanced, and I know that this reaction will take place because the zinc is more active than the hydrogen, so it can kick the hydrogen out of the compound. Now let's take a look at the other example I've given you. Here I have silver I'm trying to react with hydrochloric acid. So let's compare the activities of silver and hydrogen. So again, if I look at my periodic table, hydrogen is here. Silver is down here though. So silver is less active than hydrogen. Is silver going to be able to kick hydrogen out of that compound? No, this is not going to happen. Silver is less active than hydrogen, and so hydrogen energetically prefers to remain an ion in that compound. Well, there are a number of ways that we can signify that a reaction is not going to take place. I could put an X through the yields arrow, but another way that we're going to use is we're either going to write no reaction or NR. So I'll write no reaction. That just tells us that even though I can write a proposed chemical reaction, in this case, it's not actually going to take place. Again, in a single replacement reaction, the single standalone element has to be more active than the element that it is replacing in the compound. That's the only way that a single replacement reaction will occur. So with that in mind, I've given you 3 sample problems here. And it says for the next 3 reactions, predict whether they will occur. To do that, you need to compare the single standalone element with the element that it's going to try to kick out of the compound. Compare the relative activities. If the reaction does occur, then complete the reaction with the correct formulas for the products, and then balance the reaction. If not, if the reaction does not occur, then simply write NR as an abbreviation for no reaction over on the product side. So again, if the reaction is not expected to take place, you're not going to worry about writing the correct formulas for the products. You're not going to balance the reaction. We're just going to write NR, signifying that this reaction does not occur at all. Okay? So, go ahead and pause the video, see if you can do all 3 of those according to the directions. And when you're done, restart the video and I'll work through them for you. All right, coming back, and we're going to work on this together now. I have aluminum and HCl. This must be a single replacement reaction. I know it's not a combination or decomposition reaction because I've been asked to predict the products. And remember, on combination and decomposition reactions, you cannot always predict the products. So if I look at this, it's pretty obvious it's a single replacement reaction. A single standalone element is reacting with a compound. Yes, the compound is an acid, but that doesn't make this an acid-base reaction. So single replacement reaction, how do I know if it's going to take place? If the single standalone element is more active than the element that it's going to replace, then the reaction will occur. So let's compare aluminum and hydrogen on our activity series. And we see that aluminum is right here, but hydrogen is way down here. So aluminum is more active than hydrogen. So yes, this will take place. This will take place. And so hydrogen is going to be kicked out as an element alone by itself, as H2. And aluminum is now going to take its place in a compound with chloride or one or more chlorides. Aluminum is fixed charge at a 3+ ion. Chloride's a -1, so I need 3 chlorides to charge balance. And there's the correct formula for my products. Now I balance my reaction. Balancing the equation. 1 aluminum, 1 hydrogen, 2 hydrogens. I need 2 hydrogens. 1 aluminum, 2 hydrogens, 2 chlorides, 3 chlorides. Aha, this is that old case where I have to do least common multiple math, because there's not a single change I can make to anyone's coefficient and make the same number of chlorides on both sides. So the least common multiple between 2 chlorides and 3 chlorides is 6. So I'm going to need 6 chlorides on both sides. How do I get 6 over here? I cross that 2 out and I make it a 6 coefficient. How do I get 6 chlorides over here? I put a 2 times 3 is 6. Now I've changed coefficients, so I'm going to go back to the beginning. 1 aluminum, 2 aluminums. Let's fix that. 2 aluminums, 2 aluminums. 6 hydrogens, 2 hydrogens. Let's make it 6. 2 aluminums, 2 aluminums. 6 hydrogens, 6 hydrogens. 6 chlorines, 6 chlorines. And it's balanced. All right, next problem. Magnesium reacting with zinc nitrate. So let's see if the reaction is going to take place. I'm looking at magnesium, not manganese, but magnesium and zinc. Here's the magnesium, and it is higher on the list than the zinc. So magnesium is more active than zinc. So magnesium can kick zinc out of a compound. So will this reaction take place? Yes, magnesium is more active than zinc, so that will take place. If that happens, then zinc is alone by itself now, and of course it's going to be a solid. And when magnesium pairs up with nitrate, magnesium is a 2+ ion, and nitrate is a -1, so I'm going to need 2 nitrates. So 2 and -1 nitrates to balance that +2 magnesium. So there's the correct formulas. Now I need to balance it. 1 magnesium, 1 magnesium, 1 zinc, 1 zinc, 2 nitrates, 2 nitrates, and it's already balanced. All right, last one here. Chromium reacting with magnesium iodide. Chromium and magnesium, I'm going to compare those two. So where are chromium and magnesium? Here's chromium, but notice now that it is less active than the element that it is trying to replace. Chromium is less active than magnesium. So can chromium kick magnesium out? No, it can't, because chromium is less active than magnesium. So this reaction will not take place. So I don't need to write the correct formulas for the products and balance the chemical reaction. I'm just going to signify that the reaction does not occur, no reaction, and there I'm done. And that is how we use the activity series. I can write many possible reactions, but just because I can write a reaction doesn't mean that it is actually going to take place.